Alright, so what we're looking at today is rectangular hyperbolas. You can see on the graph at the right there that I've made a graph following a table of values. So just to explore that a bit further, we've plugged in some x values from -4 out to +4 with some fractions thrown in there, because fractions are actually a really big part of rectangular hyperbolas. So the first thing we'll look at is the actual table of values. Now, you notice that the rectangular hyperbola form is 1 over x. So when I plug in a value for x, it puts it on the denominator, which creates a fraction. So 1 over -4 is -1/4. 1 over -2 is -1/2. 1 over -1/4 is -4. And you have to remember there that when you divide by a fraction, it creates a bigger number. So you're essentially asking how many quarters are in 1? There are 4. All right, so to go back and have a little explore, you notice that when I plug in, when I look over here on the graph, -4 -1/4, then as the x value gets closer to 0, the fraction gets further away from the x-axis, all right, because that whole value is getting bigger. So this one here, this last one I've clicked, hold on, I'll turn the others off. This one here is when x equals -1/6, and 1 divided by 1/6 is 6, so then it's out here. And the smaller that fraction gets, the bigger the y value gets, as you can see by the green line just keeping on going down and down and down and down. Opposite the, over the y-axis, you can see that the same thing happens. So it starts up here where x equals +1/6 and the y value is a big number. As that fraction sits in between 0 and 1/6, the green line just keeps going up and up and up and up. And then as we work our way across, as the x value gets bigger, the fraction becomes worth less, all the way out to 1/4. So 1 over 4 is just 1/4. And then as you make the x value bigger and bigger and bigger and bigger, the fraction just gets smaller and smaller and smaller and smaller and approaches the x-axis. Now, looking back at the graph, the table of values, you might notice this middle value in here. When x equals 0, the y value is undefined. You need to remember that when you divide by 0, there is no value. It is undefined. This means for the graph that there is no possible way you can make it touch this y-axis when it's in this basic form. All right? So 1 over x will always never touch the y-axis, or, if you've noticed, the x-axis. All right? So just to show you how that works algebraically, I'll move that to the side. Over here, we have 1 over x. If I plug x equals 0 in, I have 1 over 0, which is undefined. So that tells me that when x equals 0, the function is undefined. If I want 0 to equal 1 over x, is there any possible number I could plug in place of x to make the entire thing worth 0? No. A small value for x makes a small fraction. A big value for x makes a small value for x makes a big fraction. A big value for x makes a small fraction. It will never be equal to 0. So that's just a couple of examples of why it never hits the x or the y axis. All right, so I'll bring this back. I will get rid of that text there. All right, so moving on down, we're going to have a look here at what happens when we change the top number to become a 2. So here is the purple points. All right, and I'll graph the green ones as well. So you can see the purple ones have moved further out. All right, and just to have a quick explore of those, when we plug in -4, the original one was -1/4, the purple one is now -1/2. You may notice that it's doubled what the top number indicated. So 2 over has doubled the fraction. So this one here, instead of being -1/3, is now -1/6. -1 instead of -1/2, -2 instead of -1, -4 instead of -2, that one, -8 instead of -4. And you can tell which fraction, which points to pair up by looking at the x values. So the x values haven't changed. In both 2 on x and 1 on x, they are the same x values. So -1/4 gets plugged in, -4 gets spat out. -1/4 gets plugged in, but this time it's -8 that gets spat out, so it's doubled. All right, so this top value in the fraction changes the dilation of the rectangular hyperbola. All right. So you can see that happening there. Now we'll go and have a look at a few other examples down, moving down. So the first one we'll have a look at is how we can change that number. All right, so this is an example of when it's 1 over x. Now you notice in the entry line here I've put a over x and I've added a slider in for a, so we can explore the changes that happen with a dilation factor. All right, so let's have a quick look. When I change a to be bigger, look at the blue line, you can see that it's being pushed or stretched out. All right, and I don't know the proper mathematical word to describe that. It's like someone standing with their hands on the line and pulling apart. All right, now as I make a smaller than 1, so I a fraction, watch what happens. It gets pushed in towards the origin. All right, and you notice the corner, the corner becomes a bit more square. So this area in here becomes a bit sharper. All right, and the gap between the origin and the line gets smaller. All right, so this is the dilation factor. All right, and you can see how the change happens. So moving on down, we'll have a look at what happens when we make it a negative hyperbola. So I'll leave the blue line on there to show you what 1 over x normally looks like, and then I'll show you what a negative 1 over x would look like. And you notice that it's been reflected. Now, we could put 1 over x like this, or we could put 1 over minus x, and neither of them makes a difference, and I'll explain why. If we assume that negative sign indicates a reflection, we could either reflect across the y-axis or across the x-axis. And you can pretty clearly see when I draw those arrows that if I reflect this down, it's going to become this purple line. If I reflect it across, it's going to become that purple line. So either way we wrote it, the minus out the front or the minus in the bottom, it made no difference to where it appeared. It appeared in the other two quadrants opposite them. All right, so just keep in mind that reflections go both ways. All right, so now we're going to have a look at some translations, and I'm going to show you, first of all, a 1 over x plus a value. All right, now I've put a slider in for that value so we can see what happens. So the first thing I'll do is I'll move the slider so it's bigger than 0. And you can see the black line compared to the blue one, I'll say up, has gone vertically. All right, it's gone vertically up. If I move it smaller than 0, you can see it goes down. All right, now I'll show you what happens when we want to move it across. And to do that, we have a h value, and you notice the h value occurs next to the x, just like for parabolas. And when I move this, you can see they're both blue, but one of them has moved left or right, horizontally. All right, now, getting back to the other feature of a graph, of a hyperbola, sorry, it is this idea that it will never hit the x or y axis. All right, and you notice that if I move it horizontally, it's all of a sudden it's hitting the y-axis. So there has to be somewhere we can determine where it won't hit. And that idea is called an asymptote. All right, so I'm going to turn on these. These are vertical and horizontal lines. Now normally for the 1 on x hyperbola, they sit at the x-axis and the y-axis. All right, but if I move the hyperbola up or down, all right, we can see here that now it crosses the x-axis. All right, so what has happened here is we've moved it up or down, and the asymptote has also moved up or down. So now, looking at the equation, we've got 1 is equal to k, 1 on x plus 1. All right, this means that the asymptote is moving up or down also. So we can see here that the horizontal asymptote is the same as whatever the k value is. So when k is 3, the asymptote is up at level 3 also. When k is 5, the asymptote is up at level 5 also. All right, and the same thing holds true for the vertical asymptote. All right, oops, I'll move this function here. We can see that when I move the function horizontally, the vertical asymptote moves. All right, so we know there that h is the same as the vertical asymptote and k is the same as the horizontal asymptote. And if you want to see all of them in action, I'm going to turn this function on, and I'm going to turn the sliders on to move around the screen. So we can see here that this function is moving around the screen vertically and horizontally, and moving with it are the vertical and horizontal asymptotes. So this middle point here keeps moving as the function moves up and down. All right. So the understanding you need to take away from that are that the h value, or horizontal translation, moves the vertical asymptote, and the k value, or vertical translation, moves the horizontal asymptote. All right, moving forward, just to recap, I'm going to put in a little synopsis of what we've gone through this morning. So here's the section summary from your textbook, and I'll just annotate all over it so we can see it as I go. All right, so first of all, we're looking at the dilation factor. So when that numerator of the fraction is bigger than 0, it's dilated from the x-axis, so it pushes it out this way, like that. So when you change that 1 to a bigger number than 0, it pushes it out, and we were able to see that when you change it to a fraction, it brings it in and makes that corner a little bit sharper. To reflect it in the x-axis, remember it actually didn't make a difference, but we'll call it in the x-axis, you just put a negative sign in front of the entire hyperbola, and that sends it over the x-axis like this, and this one goes up there, it becomes like that. All right, now we use the same letters to show vertical and horizontal translation as we did in quadratics, so h and k. H translates it horizontally and k translates it vertically, and they sit in the equation in the denominator and outside as the what you could also know as the c value. All right, now remember this is automatically x minus h, which means you need to read the opposite of it when you try and read the horizontal translation. This is the entire form here, which shows dilation, horizontal translation, and vertical translation. And the last thing is that you can read the vertical asymptote from the h value and the horizontal asymptote from the k value. So when you are looking or being asked to sketch a graph, you can automatically put h and k in as horizontal and vertical asymptotes. So that's x equals h, and this is x equals k. And if you needed to go back in the video and have a look at how those worked, just remember that when you translate it left and right or up and down, the two halves moved simultaneously, and therefore the center also moved, which moved the asymptotes. So quick recap there. We use the same letters as in quadratics. They show the same information. They sit in different spots, and the shape of the graph is a little bit different. But overall, it shouldn't be anything new.